Hello everyone, this is video 14.2. We're going to be looking at symmetry and some ideas of symmetry. Um, so hopefully you've watched 14.1 before, because the four rigid motions that are in 14.1 are going to be the entire basis pretty much of this video. So if you have any questions about 14.1, you may want to get those cleared up. If you haven't had a chance to watch 14.1, or you need to read through the book, but you need to make sure that you really know those four rigid motions before you start this section. So let's get started. So if we're going to talk about symmetries, then a reasonable starting point would be to define what a symmetry is. And so what we mean by a symmetry is a transformation which is going to make the shape or pattern appear unchanged. So after we've applied this transformation, whichever of the four we're going to be looking at, if after we've applied that transformation, the object, the pattern, the shape, the design, whatever it is, if we can't tell that anything's happened, we're going to think of that as a symmetry. Now, I'm going to sort of assume that everyone in the class has seen at some point a reflection symmetry. You take like a mirror and you put it on an object, and then half of the object with the other half of the object sort of make the original object. And that's certainly one type of symmetry, and it's going to be one of the symmetries that we're going to look at. But there are other symmetries, and so I think when I've taught this in the past, the tendency for some students is to look at it and go, symmetry. It's not that hard. It's just symmetry. There might be more to symmetry than you might know or expect or anticipate. So there's odds are going to be something new for just about everybody in this section. So just, keep your eyes open and your mind open to new ideas that you might see in this section. So we're going to start with the symmetry that we just talked about, and that is that reflection symmetry. And so we can think of in these pictures here, each of these lines as being a place where you could put that mirror and see that reflection kind of completing that object. And so here, if we were to put it along this line in this first object, if we were to put the mirror here, going up and down here, then this would be my original side over here, and this would be my image. And so between the original side and the reflected mirror image side, we would see this original shape. And we could take the same mirror and put it horizontally across the shape, and the same thing would be the case. So we want to think about moving beyond sort of the mirror idea and thinking about this reflection in the way that we talked about reflections in the previous section. And this would be that these would be lines of reflection instead of just mirrors. And so if we were to take this line A as our line of reflection, then we would see this point here, we'll call it K, and then L, and then M, and then we'll call this P. And so K would reflect back to itself. And so that point will appear unchanged because it's reflected to itself. And the same thing is going to happen here with M. It will reflect back to itself. Now, P will be where the image of L is, and then L will be the image of P. And so they've switched off. This can be a little confusing looking at this definition of symmetry for the first time, because sometimes students will think that the image of L has to end up at L. No, that's not the case. We want just the whole shape to appear unchanged, even though we can see clearly that by doing this reflection that this point and this point have changed positions. But because they're not inherently labeled, we don't notice any difference. We're just looking at the shape. We're not necessarily concerned about the labels. So even though the points have switched places, it's still a reflection. This shape has two lines of symmetry, so we would say that it has two reflection symmetries. Also, be careful. A lot of times students, when they see a shape like this middle shape, you'll ask how many lines of symmetry there are, and students will like to count 1, 2, 3, 4, 5, 6, 7, 8 lines of symmetry. And hopefully you see what's wrong with that. we've counted all these lines twice. So line 1 and line 5 are actually the same line. 2 and 6 are the same line. 3 and 7 are the same line. And 4 and 8 are the same line. So this shape only has 4 lines of symmetry, even though there's 8 kind of spokes sticking out from the center. The same thing is true here. This has 5 lines of symmetry, even though there's 10 lines kind of poking out there from the center. So these all have reflection symmetries. Okay, so the second type of symmetry we're going to look at is what's called a rotational symmetry. Most people, when they hear symmetry, they think of reflective symmetries, and like we just saw on the previous slide, it certainly is a type of symmetry. Not a lot of people think about or maybe even know about rotational symmetry as a symmetry. What we're going to be doing is we're going to be doing a rotation instead of a reflection. And because it's a symmetry, we want the object, again, to appear unchanged. Now, if we look at this letter H that we have here, this first example, we can see we have the center of rotation that we need anytime we're doing a rotation. So we know the two objects that we need are a center and we need an angle. And so we've got here this 180-degree rotation. Now, there's a slight error in your textbook because your textbook on page 621 says that the rotation has to be more than 0 degrees but less than 360 degrees. But on the next page, it says that because this can be rotated 180 degrees, that it should have a twofold rotation symmetry. You can't have it both ways. I mean, you have to include one or the other. So realistically, it should be that it is greater than 0 degrees, but less than or equal to 360 degrees. We should include either the 0 or the 360, one or the other. A lot of the other books that you'll see if you go online and watch other videos or look for other information on rotational symmetries, they'll talk about the 0-degree rotation or the 360-degree rotational symmetry. So either leaving the object alone or doing a full turn also counts as a symmetry. And that might seem silly, but if we were to take, say, this triangle and not include either the 0 or the 360, we would notice that it has 3 reflection symmetries. And then if we throw out the 0 or 360, it would only have 2 rotational symmetries. And that seems silly to have a triangle with the 2 symmetries instead of the 3, an equilateral triangle specifically. So that's why we include the 0 or 360, and so now we're going to have the same number of reflective symmetries as rotational symmetries. And the same thing for the H. You can notice that this is an axis of reflection, and so is this. So it has 2 reflections. Then it should have 2 rotations as well. So it has the 180, and it also has the 360, or the 0, whichever way you want to call it. Same thing's true for the hexagon. It has 6 reflections, and so it should have 6 rotations. So that's why we include the 0, 360, 0 or 360 rotation, one or the other. I know it seems like a strange thing to, like I said, to count either not doing anything or the full turn as a symmetry, but it keeps the numbers symmetrical, ironically. So it keeps them nice and balanced. So that is a symmetry to keep in mind in your rotation symmetries. So, we've talked about this a little bit here. You may have noticed that in all the previous examples, everything had reflection and rotational symmetries. As it turns out, anything that has a reflection symmetry will have the same number of rotational symmetries. So the H shape that we looked at has 2 of each, for example. The horizontal vertical reflections, and then the 180 and 360 rotations. But this doesn't work in the other direction. If something has a rotational symmetry, it does not necessarily mean that it has a reflective symmetry. So if you look at this shape, you can clearly see that it has 5 rotational symmetries. This point could move here, 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 or this one could rotate all the way around to there. So we've got 1, 2, 3, 4, 5 rotational symmetries. But there's no reflection symmetry. There's no reflective symmetry to this. There's no reflection that creates a symmetry here, no matter how you draw the line. And so this relationship works in one direction. If it has reflection, it has rotation, but doesn't work in the other direction. If it has rotation, it doesn't necessarily have, if it has rotation, it doesn't necessarily have to have the same number of reflections. And there are some objects that have rotation without any reflection at all. This is important because I think a lot of times when students are categorizing things like this, they like to think, well, if it has one, it can't have the other. And as we'll see later on, we're going to have shapes, designs, whatever, that have more than one symmetry. So we need to consider all the possible categories and whether or not any of these match. So you might be wondering, how could translation or glide reflection create symmetries? In order to do this, we need to look at some larger patterns. And so we're going to be looking at one-dimensional patterns, which are called freeze patterns, or sometimes you'll see referred to as a wallpaper border pattern. And so this picture on the left sort of shows wallpaper borders. And so you can see here that we've got the same thing kind of going one after the other. And there has to be some sort of repetition to it, or else it wouldn't be a pattern. If you had a wallpaper pattern that didn't have a pattern to it, then it's not really going to fit into what we're talking about. So the implication is that there is some sort of repetition to it. Keep in mind, it's also possible that we could look at this same idea on a two-dimensional pattern. Um, these are often called wallpaper patterns. I'm just mentioning that this is a possibility. Again, depending on where you look for help or assistance on this topic, you may see this idea, but we're not going to talk an awful lot about that in this class. These two-dimensional patterns, these wallpaper patterns, however, I will mention, are understood to be infinite. And so this wallpaper is going to keep going in all four directions. Now, if you've ever seen a roll of wallpaper, I mean, you know it kind of it stops. I mean, it's finite. There's not actually like infinite wallpaper. But even if you look at the wallpaper itself, it comes in strips, and so it's easier to think of as being infinite in one pair of directions, but not the other. But the idea is that we have an infinite number of infinitely long wallpaper strips, and so it creates an infinite plane of these objects. Again, we're not going to get too much into this, but just in case you look at it and you're curious, that's what's happening with wallpaper patterns. So let's look at the first example, in that being a translation symmetry. And so a translation symmetry is going to be almost the exact same definition that we saw for reflection and rotational symmetry. Is just we're applying a translation. And so we're going to want to do a translation, and we want the design to appear unchanged. Now, as I mentioned before, this is understood to continue in both directions here, left and right. So this is infinite in both directions. Now, it's not infinite along the top, and it's not infinite along the bottom. It's just kind of moving along this one-dimensional um, line. So it's going in those directions. Now, there is translation symmetry here, but we got to be careful how we translate it. So let's say I look at this blue point right here. So remember, for a translation, it's defined by the vector. It's defined by the line that sort of describes how it's being moved. If I were to move like this, that creates a symmetry. And so now each of those blue points will slide over and make the next blue point. And so it will appear unchanged. Now compare this to, and let me do this in sort of, no, I don't want to do that. We'll do it in this sort of purple. So suppose instead I go from this point over here to this point. Now, that's not going to be a translational symmetry, because even though these dark points along the top will match, notice that this black point and this blue point have switched places. And so this black point will move over to here, and this blue point will move over to here. And so now I can tell that it's changed. It looks different. So the vector is hugely important. The way in which we're translating it is going to be really important It has translation symmetry, but we got to make sure we translate it by the right amount. This yellow vector, by the way, is not the only possible vector. I could also go, I'll go from here all the way over to here. So I could move it 2 spots over, and that will create a translation. I could also, I'll switch to red, I could also go from this point back, so I can go in either direction. So again, I'm going from this point to this point. But I got to make sure that I'm being very careful about how long and which direction I'm translating. I want to make sure everything matches, not just one characteristic like this up here. Everything needs to match so it appears unchanged. The last one is glide reflection. This is our fourth translation to look at and how it is going to create a symmetry. So there's an example here along the bottom. And so you'll see here that one thing that I could do, I've got this brown point here and this brown point here. And so I could do my reflection, so take this and flip it up this way, and then glide everything over one square. So now this brown point flips to the top, and then it moves over, so it flips to the top and then moves over to this spot, and so now the brown matches up to this brown. Now, if we look over here, the same thing's going to happen here. We do the reflection. Again, the line of reflection here is going right through the middle, horizontally through the pattern. So once I do the reflection, this brown flips down here, and then applying that same arrow, it moves into this brown spot. Or we could take this purple, and then it reflects over, and then it slides over. So there's my reflection and my glide, so purple matches up to purple. Everything else matches up. Again, we're thinking about these as being sort of infinite patterns. So this is still continuing to the left and to the right. And so if I were to do this brown and flip it over here and then slide it over, it matches what would be here, even though we're not showing what's there. We can see from the pattern, we understand what would be in that spot, and we can see that it would be a brown there, so it still matches. Now, you might notice again that this pattern has a glide reflection, but it also has a translation. And so again, having one symmetry does not preclude it from having other symmetries. So this also has, and I'll do this in, I'll do it in green for whatever reason. I could take this brown point here and slide it over this far to here. So it could have just a translation. So again, like I pointed out, having one symmetry doesn't mean that it can't have others. Now, if you click back to the previous slide, you'll see that that pattern has translation, but does not have glide reflection. As soon as you flip that pattern over, you've got the points that were on the top now along the bottom, and the points on the bottom along the top. It won't possibly match no matter how you glide it left or right. So again, if it has glide translation, it also, or glide reflection, it also has translation. But if it has translation, it doesn't necessarily have to have glide reflection. It might, but there's nothing that says it necessarily does. So I'm going to show you this little chart here, and there are only 7 different types of border symmetries. And I like this little picture here because it's got feet, and so we could think about kinesthetic ways of students sort of like hopping on one foot to show that translation symmetry as we sort of move along. Number 2 shows translation and glide reflection. And so you can see how these feet have symmetries based on this translation, but also the reflection. We can also reflect and move it a half step. So once this reflects, it's going to be sort of in between. So it moves a half step to match up there. Don't memorize this chart. And depending on where you look, all 7 of these have names. Don't bother memorizing those names either. The only reason why I'm bringing up this chart is to show you that there's only 7 of them. But more importantly, I think, is to show you that a lot of these groups have more than one symmetry at a time. In fact, the F5 group has translation, glide reflection, and rotation. that infinite pattern can be rotated around. And so we put the point here, for example. And so when we rotate that infinite strip, this is going to match up down to here, and this is going to match up to over there. And so this whole infinite strip can still be rotated and have a symmetry. And so we're going to have these that have more than one symmetry at a time. Again, the natural tendency for students, once they find one, they just assume the rest of them don't exist. Clearly, that's not the case. So for your checkpoint, here is a border pattern. Again, this is going to the left and to the right infinitely in both directions. So which symmetries do you notice this pattern having? Does it have reflection? Does it have rotation? Does it have translation? Does it have glide reflection? So I'll let you look at this pattern and try to figure out which of those four symmetries it has. If you have any questions about this problem or anything else from this section, by all means, please bring those questions to class and we'll get them answered. All right, thanks.